Okay, thank you. There's no AI in the title, but I promise there's going to be a little bit of AI. I'm not sure if it's, I would call it cutting edge. You'll see it's going to be a very basic multi-layer perceptron, but I believe it's a nice example where in a specific application that has come up in this Climate Futures SFI, we were able to solve a problem that used to be a lot more difficult by the software that is now available, things like PyTorch and Keras, that make it very easy for people that have a general data science background to use this technology. So here's the background for this project. As Ole and Etienne have explained in this Climate Futures SFI, there's a number of researchers working together with industry partners, and in our case this was Statkraft. And one of the problems that one of their teams was working on was the prediction several decades into the future of energy prices, because that will inform some of their investment decisions. Here it was specifically about hydropower, but of course this also has implications on other investments. So for example, if the prices go up but the hydropower production becomes more difficult and there's some things that point towards that, then investment decision could be to just build out wind energy over Brazil. So, so they were interested in the prices, but of course that comes down to predicting how much water is there going to be in Brazilian catchments. And the team in Statkraft that is working on that has, within this Climate Futures SFI, approached us to work together on this problem. So why is there like a long-term prediction necessary? Well, the climate is changing, as you know, and in Brazil there was actually relatively dramatic changes over the last 2 decades with inflow over some of these catchments. But of course, some of these things go a little more complex, so it could be that in some months inflow increases, in others it decreases. And there was a desire to just understand these changes because they would influence the prices in different times of the year. The first question is then, well, do you have to reinvent the wheel? Isn't there already somebody out there who has offered these products? And there is, in this case, the Swedish Meteorological Service has a product called HypeWeb. Over the Nordics, Statkraft actually does this themselves. Like they have very good hydro models, and they would just run this themselves. But over Brazil, where they're also active, they don't have that. And so they were looking at that data product. And over some areas, when they just did some analysis of what did this product produce in the past, this looked pretty reasonable. But then there were some cases where there were some questionable features about this particular product that made them doubt whether it's useful for their purposes, where some trends that have been observed were going the opposite way of what this model is predicting. And while this is related to the general challenges of using and interpreting climate model output, there was this additional issue that even very basic statistics just didn't match up. And also known trends in the climate weren't really reflected by these models. And this is what started this particular pilot study in this Climate Futures SFI, where we were just wondering, well, if we don't have a hydro model over that area, can we build a simple statistical model that can help us get these decadal projections of inflow? The data that we used for that was inflow data from like around 155 catchments. We use different data products for temperature and rainfall. And this is only relevant insofar as this CHIRPS version 2 product is kind of the bottleneck as far as data availability is concerned, because that is a relatively high quality precipitation product that is based on satellite data, and because satellites have only been around for a few decades, we can't go further back in time. And that is relevant for statistics because we always like more data, and we don't have that because of that particular limitation. And that will come up later again when we talk about the statistical modeling. And finally, of course, the key ingredient here is output from these CM6 climate models that Etienne has mentioned in the previous talk. So this is a whole collection of different climate models built by different centers, and the reason for using different models is that they may have different biases, and there is a lot of general variability in the climate system, and the hope is by looking at the whole collection, at least some of these variations kind of average out a little bit, or are like represented in an appropriate way. Here you see just like a map of some of the catchments. There's actually a lot smaller ones still that are not included here, but this gives you a general idea that the catchment sizes are very different, and this will also become relevant in the modeling later. Our first iteration was a very much not AI model. It's a relatively basic regression model for two reasons. First of all, even in the AI era, it's always a good idea to start simple and only move on to a more complex model if you really need to. That is a general statistical modeling principle that is still correct. And when we did some exploratory analysis of the predictors and predictants and how they relate, it seemed like a linear relation isn't all that inappropriate. Second point has also come up in Stefan's talk this morning, is one of the things that make people a little bit reluctant adapting AI models is their lack of interpretability. And especially when you talk about something like climate projections, where you're kind of extrapolating far out into the future, you get even more uncomfortable if you have to use a black box model that takes in a few numbers and spits out a few numbers, and you don't really get a good intuition for like how it got there. And for these two reasons, we thought, okay, let's start simple, use a regression model that is trying to model anomalies of inflow based on anomalies of temperature and precipitation at different time lags. Like the latter is because there's some inertia in the system, so even if you want to model, say, July precipitation, then what happened over the last month will have an impact on the inflow in July. And we put in a few constraints in the model, I think, which is not very important here. The reason was that we already saw that overfitting could be a little bit of an issue, and we didn't want to get any relations that were completely unphysical. So over Brazil, the effect of temperature is mainly through evapotranspiration. So unlike over Norway, where higher temperatures typically mean more snow melt and therefore more inflow, over Brazil it's the opposite. They evaporate more water, they actually get less inflow if the temperatures go up. But for precipitation, of course, we expect that more rain leads to more inflow. And so the idea of this model is that in the first step, we want to build a model that relates these variables that we can get as output from a climate model to the variable that we're interested in, which is inflow. And then in the second stage, use the climate model output to tell us what is the inflow going to be in the future. And here's just like a result of how much of this inflow variability can we explain through the regression model, just to get an idea, is this link even working? Because if that is not working, then our whole climate projection is going to be questionable. And you see over during some seasons and some areas, like we did struggle. I don't think it's our model. We have had a lot of discussions about that. Why, for example, you see here over large parts in Brazil in July, the explained variability is relatively low. And this could be due to all sorts of reasons, from limited data quality, but also things like deforestation or changed land use that have changed the response of the rivers to the meteorological inputs, and therefore make it difficult to get a good model. So over these areas, and I will come back to that, we will always have a challenge of making a good projection. But you see over a lot of areas, luckily, we can explain inflow through this relatively simple model by these meteorological variables that we can simulate with a climate model. So here was the concern, and here's where the AI comes in. So different regions respond very different to these variables. We've just seen that, and also at different times of the year, the model is different. And that means with only 40 years of data and a separate model for each of these catchments and each month, you're fitting a model that is quite simple, but still has 4 parameters to 40 years. That's kind of at the limit of where you want to fit your models. And if you look at what these regression coefficients look like, you definitely see some questionable things here. So for example, the response to temperature, again, recall that here we're talking about evapotranspiration, which is not something you would expect to vary dramatically over different areas. And you see that some river forks here would suggest that they respond quite strongly to evaporation and changes in temperature, and others not at all, that are right next to them. So that is physically very implausible and would just point to the model being overfitted. And so you see this for different months. And so that was the point when we felt, okay, maybe the model is still a little bit too simple, and we have to try something to fix that. And this is where I said, like maybe 10 years ago, probably some spatial statistics model would have come to my mind to address this thing and address this issue of can we not link those different locations in a smart way. But this actually gets pretty complicated because I've showed you we're dealing with very different catchment sizes. So spatial proximity is only one of the variables. Like you have to deal with a lot of other things that determine if 2 places are similar and you should expect like a similar response. And so luckily we didn't have to go down that road, but because of software packages like Keras and PyTorch, it's relatively easy now to build a neural network model that does all these complicated things for you. And so as you see, that this is a very basic multi-layer perceptron architecture, so nothing new. These have been around for 30 years. One thing that you'll note is a little bit unusual about this architecture is that the actual predictors aren't going through the neural network. And that is because the point I've made before is still true now, that we want something that is interpretable, and neural networks are notoriously not, or at least not in a straightforward way. And I've already argued before that the predictors, that the relation of these precipitation variables and temperature is actually relatively linear and relatively benign. The part that's complicated is to figure out for a particular month and a particular catchment, what should the regression coefficient be, if you don't just want to fit a separate model. And this is where we kind of use the AI for. So we just give the neural network model an index of the month and an index of the catchment, no other information, and use this whole machinery of embeddings and now a nonlinear relationships, and like through all these things that you know, like these different neural network layers, to kind of figure out for each particular, or for a given location and a given month, what is the proper regression coefficient. And the reason why this works better is that through this machinery and through linking them all together in one model, as opposed to 1,000 different like simple regression models, is that now all these things are connected, and this gives us a certain regularization. So one of the things that neural networks are really good at is that they have lots of parameters, but they also have machinery in place that regularize things in exactly the way that we wanted to prevent overfitting. Yet at the same time, we still have our basic regression model at the end that we can look at and interpret and see if it makes sense before we get our inflow projections. And so here's just one example of how the regression coefficients look now if we use the neural network model to fit them. The top row is the previous model, where I've argued that some of the coefficients that we see, especially for temperature, but if you look close enough, then also for the other variables, just don't make physical sense. And at the bottom, you see how this would look if the neural network model does the model fitting through these embeddings of locations and month. And you see exactly the thing that you would like to see to get a little more confidence in our model. They still reproduce the same structure, maybe a little bit dampened, but they don't have this spatial variability that we've seen for the regression models that doesn't seem plausible. And so I think I have another example here. Like, can go through these different things and just like look for features where the regression model produces spatial variability that seems unrealistic, and the neural network model basically manages to smooth that out while still giving us the capability of adjusting to different catchments that kind of different sizes, different climate zones, and to different times of the year. So it was just basically a tool that is simple to use to fit a regression model, that is interpretable. We can look at these coefficients and have these discussions of is that plausible or not, and do this within the machinery of a neural network model. And so then the next step, coming back to the project objectives, would be how do we get from there to a climate model, to a projection of inflow. We now use the climate model output. We take simulations of temperature and precipitation from that climate model, and that's the whole separate discussions of how accurate or how representative that is. And there's some caveats and points to consider there. But assuming that, at least as a collection across like a number of different climate models, they give us some idea of where the trends for precipitation and temperature go, we can now plug this through our model to see what are the trends that we see for inflow. So here's some example that is specifically picked to show you both the good and the bad aspects. There's a lot of lines here to explain just the most important things. This really short line is kind of our fitted model. The reason why it's so short is that we have taken 30-year averages, which is one of the things that you usually do when you interpret climate model output, because the climate model, even when you run it in the past, is kind of detached from reality in so far as it doesn't try to reproduce the actual weather that has been. It just tries to reproduce the appropriate climate system and kind of simulate what could have been in this climate. And so you have to average over longer time periods to filter out kind of this variability over shorter time scales and get a longer term trend signal. And so that's why our fitted model curve here is so short. We do have inflow data further back. So by comparing those two, like the red and the purple curve, we can kind of see how well is our model doing. And as I've shown you, in some regions, we already see that the model can be expected to do very well because of other factors. There doesn't seem to be such a tight connection between inflow and precipitation and temperature. And you see this especially in July, where like these two curves, they don't match perfectly. And then the other aspect is, of course, now you run all these climate models through this model, and you kind of see historically how well did it reproduce what you observed, and you get an idea of at least some of the uncertainty going forward in the future. This isn't uncertainty quantification in a strict sense, because there's so many more things we're uncertain about the future, not least like what is going to be the future emissions scenario, all sorts of questions around the climate models, and the variability that is just natural and that kind of blurs any systematic trend. So this only gives you some idea of what could happen. And so as you can see, for the months where the model was struggling, then also the historic simulations don't capture the range of what we observed as an inflow trend. So like this pretty dramatic decrease of July inflow over this particular catchment that we've seen wasn't reproduced by this methodology. But you see over other seasons, and also if you go through the different regions, over many regions, you can get some confidence that we were historically able to reproduce kind of the different scenarios, and that gives you more confidence about the projections that you're making that will then be used in some price model. So here's just some of the trends that you get out of this model when you now look at this whole scenario of climate model, the whole range of climate models, and run it through this statistical model to get inflow predictions, and just the median scenarios of what is the change expected based on these projections. And so you see for like a month selected in the Brazilian summer and fall, I guess. There we see a decrease over most of the places. Over other months, you see like a different scenario. So for example, in October, you see it's regionally different. You still see a pretty dramatic decrease over some places, but an increase over other places. But could just be that like whole weather systems are expected to shift in the future and just shift the precipitation patterns and the resulting inflow. So here's just my summary slide. I've showed you like we have this like very specific problem that one of our industry partners came to us with. We started out with a simple regression model and ran into some issues like overfitting, which is not unusual in statistics, but the use of AI methodology then allows you to solve these problems like in a relatively simple way, but also in a way that doesn't rely on this kind of black box prediction, but still gives you interpretable results that you can show and discuss with your partners and get some projections for the quantity that they need. And with all the caveats that I've shown even in these pictures about some of the features in these projections, we believe that that was useful information that Statkraft can use to inform their future investments. And that was it. Thanks for listening.